Hi everyone, we're Ram Pump, and I'm Ching.
I'm Allie.
I'm KK.
I'm Peyton.
So, the purpose of the ram pump is to, the purpose of the ram pump is to mechanically redirect a portion of the treated water from the bottom to the top of the plant. The treated water pumped by the ram pump is used for internal plumbing and chemical stock tanks within the Agua Clara plant. The chemical stock tanks contain coagulants ready to be mixed with the treated water. Currently, in Agua Clara plants, plant operators must carry buckets of water manually up to the plant. The ram pump automates this process without the need for any electricity. So this shows a cycle of how the ram pump operates. And so the plate is initially closed, and the plate is initially in an open position, and the force of the water from the driving head pushes the plate into closing. When the plate is closed, high pressure builds up and forces the water out through the effluent valve. As the water is forced out through the effluent valve, pressure decreases and causes the water to decelerate. The decreased deceleration of the driving head decreases the force of the water on the plate, and the spring force is able to overcome the force of the water and open. The cycle repeats as long as there's consistent driving head.
So here's a picture of our experimental apparatus. At the bottom, you can see our ram pump in orange. So the system KK was just talking about, that's at the bottom. And what we have simulated here is water coming down through the head tank, which is the process after filtration, through the drive pipe, through our ram pump, and into the waste bucket, which simulates distribution tanks in our Clara plant. Also at the bottom, we have a sump pump, which pumps water up to the head tank and helps us achieve a constant level of head within our head tank for calculation purposes. Back at the bottom, we have an air chamber, which helps us record the pressures that the ram pump is creating while pumping water that's coming through the drive pipe. And this whole setup is integrated into our workbench just for convenience sake, and also just take up a little less space. Here's a picture of our new experimental setup. So all the stuff that I mentioned before is in this picture. At the bottom, you can't really see it, but our sump pump is there in a waste bucket, and it didn't show in the last picture, but after water goes through the air chamber, it is pumped through some tubing to another pump, which calculates the amount of flow of water that we're getting pumped by the ram pump. And using Procota and PID, we get to use those calculations to better improve our performance of the ram pump. So from our previous design, some difficulties that we had was that, first of all, the original design was a 2-check valve system, which had a compression spring in the middle, and the only way to adjust that spring was to take the whole apparatus apart and adjust the bottom stopper, which controlled the position of the compression spring within the 2-check valves, and that would either increase the amount of force that the plate applied on the water coming through the drive pipe, or decrease it depending on which way you adjusted it. The biggest problem with that was that in an actual Agua Clara plant, the ram pump is in the basement, and sometimes the basements can be flooded, and that's not very convenient for operators to go down into and actually adjust this small piece. So this difficulty led us to create a new design, which is not in the basement, is easier to adjust, and only uses 1-check valve, which can be adjusted not in a hard place to reach. And Ali will talk about this.
So the main part of our redesign was this new spring system that we implemented. So now, like Peyton said, we only have one check valve that you can see on the right, and the plate inside of it just has one nut at the bottom to limit its upward motion. And it also has a hook at the top that connects to a metal wire that runs up through the drive pipe and then connects to this spring system that will be at the top of the head tank or in an aquifer plant above the filter channel. And so the main purpose of this spring system was to make it more convenient to access, and it also allows adjustments while the ram pump is running, so you can get instantaneous feedback and know how to adjust the springs from there. Another main point of this new spring system was that it allows us to adjust the forces on the ram pump independently. So when the plate is open versus when the plate is closed, those forces from the springs can now be adjusted independently. And the way that this all works is that we have these two outer springs that are longer and weaker, and they're connected to eye bolts at the top and this bottom plate at the bottom. And so the eye bolts can be moved up and down using those nuts. And the middle spring is also connected to an eye bolt, but through a string that has slack originally. So this way, when the plate is open and begins to close, the only springs acting on it are the outer springs. And then as it's closing, eventually the string slack runs out, and the middle spring begins to extend as well. And then once the plate is closed, now all three springs are acting on the plate. And so this really helps us out because a lot of the difficulty that came in previous semesters with trying to find the right spring for the ram pump came in these two positions being connected by one spring. So now with independent adjustments, it is much easier to use a wide range of springs, and they can then be adjusted for the specific plant and the specific ram pump. And here's a video of the ram pump in operation.
So this semester, after finishing the setup for our new experimental setup, we have conducted a couple experiments while keeping our side springs the same and changing our middle spring in the ram pump system. And in these couple experiments, we have observed an increase in total flow rates comparing with previous semesters. In previous semesters, the highest flow rates that we have achieved is around 18 milliliters per second. However, after changing our system to a 3-swing system, we've observed the highest flow rates. For example, in this figure, you can see that the highest flow rates that occurred at the 5th turn is 24.683 milliliters per second, which is a huge increase for about 6.6 milliliters per second. And we have also come up with a convention by adjusting the spring force using the number of turns that we are tuning from the eye bolt. And so changing the turns on the eye bolt would change the amounts of tension that the spring is in, and thus changing the spring force of our entire system. And you can see that from this figure, there's a general trend of the flow rates increasing very gradually in the beginning by the number of turns, and then drop significantly from the fifth turn and onwards. However, in another experiment that we have conducted, where we have obtained the highest flow rate that's around 26.75 milliliters per second in the second turn, which is toward the beginning of our adjustment, and then the flow rate has gradually decreased and then dropped significantly since the 11th turn. Therefore, this is the highest flow rate that we have obtained in this semester for 26.7 milliliters per second, and this is by changing the middle spring to a different spring while keeping our side springs the same as our previous experiments. However, we're still not quite sure about the general trend in spring force versus flow rates in our experiments, and this is just due for next semester to investigate. In the future, other than investigating the relationship between flow rates and spring force, we would like to improve our lab setup for an even easier adjustment of spring force, so that the person adjusting it doesn't have to go up to the head tank to adjust individual nut. And by doing that, we are hoping that we can introduce a correct mechanism into our spring adjustment. And in addition to that, we would also like to analyze the effect of changing and tuning the middle spring versus the side springs. This semester, we have only changed the middle springs while keeping the side springs the same. However, next semester, we will hope that next semester, teams can experiment the effects of only changing the middle spring versus only changing the side springs to see if there's a significant difference in the trend in flow rate. For long-term goals, we would also like to, in the coming winter, we would like to implement the first prototype of ramp pump, our vertical ramp pump in Honduras, and then upon feedback from the plant operators in our agua clara plant in Honduras, we would like to improve our design for an even easier operation. If you have any questions or recommendation, feel free to contact any one of us from email.
Thank you for your time.
Thank you for your time.